Welcome back to the course of process control. Let us continue our discussion about the aspects of process control system design. The procedure of process variable classification, which we discussed in previous video, becomes very important in practice, especially when initiating a control design project. During the design of a control system, engineers usually start by formulating the operational objectives. Naturally, this involves translating generic objective statements into specific control objectives for the process in question. For example, maintaining pressure of a reactor within specific range. Next, we will need some means to monitor the performance of the process and observe how it may respond to actions by the control system. This is accomplished by measuring the values of certain process variables, for example, temperature, pressure, and compositions. It is evident that we shall directly monitor the variables that represent or indicators of the control objective, and this is done whenever possible. Once the control objectives are specified and the measurements are identified, the next question is how we can cause a change in the process. In other words, what are the variables to be manipulated to achieve the control objectives? Usually, we have many options in this selection, and our decision may affect the quality of the process response, that is, the control performance. Control configuration is the information structure used to match the available measurements with the available manipulated variables. Normally, we will have many possible configurations. If a human operator implements the control action, it is a manual control scheme. If the control mechanism acts without current information about the status of the process, it is an open-loop control scheme. If the control mechanism anticipates the effect of the disturbances, producing a corrective action, it is an anticipatory control action or a feed-forward control scheme. If the control mechanism acts using the information fed back from the measured outputs, it is a feedback control scheme. What is best for a given problem is a critical question for the quality of the control system and is problem specific. As the last step of designing a control system, the controller requires tuning. The question here is how the information taken from the measurements is used to adjust the values of the manipulated variables, and the answer constitutes the control law, which is executed automatically by the controller. As we shall see later, tuning implies determination of the parameters of the controllers. Let's return to our previous example about stirred tank heater. Say we want to prevent liquid overflow. Our operational objective would be controlling liquid height. We can measure liquid height, volume, or even inlet stream flow rate as a means of monitoring the tank condition. Next, we know that in order to control liquid height, we can adjust the inflow F0 or outflow F. Each option will have different effects on the overall system and control performance. After deciding on the measured variables and manipulated variables, we usually have good estimate on which configuration we will use, whether we go for feedback or feed-forward, and whether we will adopt the single input, single output configuration or multiple inputs, multiple outputs configuration. Finally, we will be faced with which controller we need to use and what value of the controller parameters are. This is the end of this session. See you again in the next session.